here is our second extra acid base problem that we're going to work. This one is slightly different because the first one gave us the concentration and the pH. This one is going to give us the concentration and the percent ionization, and here I've designated this weak acid as HX. Again, doesn't matter, but I'll keep with the same terminology. Okay, so again, it's a weak, so we're going to have an ICE table associated with it. We're given the concentration, and again, we pretend initially that there's no dissociation. But we know that it is going to dissociate, and it's going to dissociate X amount. So we have 0.25 minus X, X, and X. Again, we're looking for the Ka of the acid. Now, in this particular problem, we don't have the pH. The additional information we're given is the 35.3% ionization. Well, percent ionization is a standard identity, but it is the conjugate, so in this case X minus over the weak, whether it's an acid or base, times 100. It's very important that you use the conjugate, not the proton, because in polyprotics, if you work polyprotics or if you work two acid systems, then you have two contributing, at least, species to give for the H+, so that doesn't give you an accurate dissociation. So here we know it's 35.3% is equal to X minus, and for the HX we use what is called the formal charge. Now the formal charge is pretending no dissociation. So we pretend that this, I can't spell dissociation, forget it. Dissociation, okay? So our undissociated species is 0.25 molar. So as we do the math, our X value comes, X minus value here, concentration comes out to be equal to 0.08825 molar. So we know that all the X values, which this is going to be H plus, as well as X minus, are those values here. So we could put them in for this, 0.08825. Now, this value at equilibrium, we do the math on, and we get 0.16175 molar once we do the dissociation. So our Ka, and again it's an acid, so it's a Ka, is going to be H plus times X minus over HX, which we now know is 0.08825 molar squared, divided by 0.16175 molar. Now, we run the numbers and we find out our Ka here is 0.04815, okay, or 4.815 times 10 to the minus 2. So this is actually a relatively strong weak acid. And we know that by looking at the percent ionization. The higher the percent ionization, the stronger the acid. Even though it's weak, remember the difference between strong acids is they dissociate completely, whereas strong weak acids still have an equilibrium, but they dissociate more.